Hello student, welcome to today's session. So today we shall be discussing, we are into the continuation of the second session of salt analysis. In the last session we talked about the grouping of anions, how they are being grouped. So there I talked about this in length. You better, those who are seeing it first time, I just would advise you to see the last lecture. Although I am giving you a slight idea what we discussed in the last session. So in the last discussion we said that when you are wanting to categorize the anions or the acid radicals into the grouping, you have to take into account chemically there's three behaviors: acid behavior of anions, and then if I would say sulfite ion or thiosulfate ion or carbonate ion, these are basic species, they eagerly would react with the acids. And then we talked about the redox behavior, that there are some anions which tend to act as a reducing agent like iodide ion, nitrite ion, they are good reducing agent. On the contrary, there are good number of good oxidizing anions also, like chromate ion, dichromate ion or permanganate ion, or there are some which can go both ways, just like nitrite or sulfite. These happens to go both way, they can increase or decrease their oxidation state during the reaction. And lastly, the most important is the precipitation, that all of these anions we would like to precipitate them in such a way that we could group them in such a way that thereafter the segregation becomes easy. So most importantly, most of the time we generally would use AgNO3 as one of the most important precipitating agent, because it readily precipitate most of the anions there in the syllabus. And then barium chloride, lead acetate. As we proceed in this session, we will be now, so in today's session is more into a specific analysis of anions, specific testing. But before I go to the testing, let me recall what we did last time. Just like these three properties are to be when I talk about these three properties are to be analyzed in such a way: first you do precipitation, then you add acid, or first you add acid, then do the precipitation, and thereafter whatever anions are left in the filtrate do its redox reaction. Something like this it is to be. Now that depends how the question is being framed in the paper. Just like this is the last discussion. Last time we grouped the anions in such a way that if we are being given these anions, I treated it with dilute sulfuric acid. With dilute sulfuric acid, some of these would release gases, just like sulfite, carbonate, sulfide, nitrite. These would react with H positive and evolve out some gas, just like SO3 2 negative would evolve SO2. And in the today's session we will be discussing sulfide would react with H positive to give you H2S, and sulfite would react with H positive to give you sulfurous acid, and which on decomposition gives SO2 and water. This way this particular discussion we had last time also in detail, so I just would refer you to go to that one. So these are the anions which would not react with dilute sulfuric acid. And then what I can do is, then thereafter I added AgNO3. So this AgNO3 is added to a solution which is acidic, because the sulfuric acid is there, dilute sulfuric acid is there. In that we have to see AgNO3 would precipitate who? Most of the anions which are of weak acid dissolves in strongly acidic medium as their silver salt. So we have seen in the last session that these are the, if some sulfide is there, that also get precipitated here. So this is the one group we generated, group number 2. These are the anions of group number 1. This way we did last time, if you could recall. And thereafter in the filtrate these are left, and in this filtrate if you just would make it basic by adding ammonia and AgNO3, some of the filtrate containing these anions also got precipitated here, like phosphate, chromate. Sulfate can also precipitate. If the starting solution has a good amount of sulfate into it, then it can precipitate, otherwise it can remain in the solution as nitrate. So this is the way we discussed, although I talked about all this discussion very fastly, but I just would recommend, because this is discussed in length in the last lecture. Now in the last lecture I do gave you one question also to address here with. I said that in the next class I will discuss it. Just like if you are being given these anions in the paper, you are being added barium chloride. Now you have to see who among these would get precipitated as barium salt. So we will see in the residue 1, if I would talk about residue 1, here what I would see here is that barium sulfite, barium phosphate, barium phosphate, barium phosphate, then barium carbonate and barium sulfate. All of these get precipitated here because we know that the salts of chloride, bromide, iodide as barium, chloride, bromide and iodide would remain in the filtrate. These would not precipitate as barium salt. Now if I just would add here dilute HCl, here if I would add dilute HCl, now the question arises here, when you just would add dilute HCl into residue 1, what you would see in the residue 2 or into the filtrate 2? Now this is an important question. Now here you have to remember, that is what I am referring to, that in the anion analysis, which way the things are being done, whether they have added precipitating reagent first and thereafter acid, or vice versa, something like this. You have to, in the IIT advanced paper, this you have to take a call. So there is no strict ruling for anion grouping as we are going to see in the cation segregation. There you have a set of rules which would be adopted every time during any precipitation. So coming back to the question, so we would see that what I just have spoken, that these are the salts which got precipitated. So barium sulfite, barium carbonate and barium phosphate. Now here is a very interesting point. When you put these all into dilute HCl, all of these would dissolve. All of these will dissolve. The fact of the matter is, why they are dissolving? The dissolution is because of this thing. Sulfite ion, if I would just explain the one, barium sulfate breaks into barium 2 positive and sulfite ion, and this sulfite ion is a conjugate acid of a weak acid. So it eagerly would react with H positive and change into H2SO3. And if you just would, because this protonic acid is not very stable, a mere of heating would evolve out SO2 gas. And once this SO2 gas, if I would show all the steps in equilibrium, what we can show here is this equilibrium would be highly forward driven, because the escape of SO2 will shift this equilibrium this side, this equilibrium this side, this equilibrium this side. So making a point, I do write it here that if I would say anion of a weak acid is soluble, or rather I would write salt of anion of weak acid is soluble in strong acid. This always you have to remember. That similarly, if I would go for carbonate ion, barium carbonate, that do also behave like the same thing. So it will change into carbonic acid, and this will easily change into carbon dioxide, and this again get dissolved into the barium carbonate, also got dissolved into the acidic solution. Now the point here is that what about the case of barium phosphate? In the case of barium phosphate, the phosphate ion tend to take H positive and change into its conjugate acid. This conjugate acid is a weak acid. This again is a weak acid, and the on its dissociation, the quantity, this is again a weak acid, as I am saying. So since it is a weak acid, and in the previous two cases, the problem had been that as soon as you add H positive, there is an evolution of gas taking place. Because of this evolution of gas, this equilibrium gone forward. But in the case of phosphate, it turned up to this particular species, and this particular species would not dissociate to a much an extent further. So point here is this equilibrium also got shifted towards the forward direction. But now we are left with what are the options there in that question. Let us check that out. So we said these get dissolved into dilute HCl. But when you talk of barium sulfate, make it a point, barium sulfate's solubility in water is very less. And if you just would add it into dilute sulfuric acid, although the solubility would increase, but the solubility is not that much to make the precipitate soluble. So the make it a point, barium sulfate you would get here with, and in the filtrate you would find sulfite ions, but primarily it get converted into SO2, carbonate ion, and HPO43 negative. These are the anions which may be present in this particular filtrate. So ultimately what you are left with in the residue number 2 is the barium sulfate. Make it a point, let me speak it once again. Barium sulfate's solubility do get increase in acidic solution because of the fact you would get barium plus sulfate ion, but sulfate ion is a very, very poorly basic. It is poorly basic, so it has very least a tendency to pick up H positive and change into bisulfite. Since it is poorly basic, so this equilibrium would not shift to not to that much as in the previous cases. And if I compare barium sulfate solubility in water versus barium sulfate solubility in acidic solution, we definitely would say it is more. But in the acidic solution, it has been seen that barium sulfate residue actually don't dissolve much. So we, in this particular question, we will answer the question as an answer to residue number 2 is barium sulfate. So what I am trying to explain it once again, last time we said the grouping in this fashion also, that we grouped the things in acid radicals as group 1 and group 2, where first we talked about dilute sulfuric acid. Any anion with dilute sulfuric acid, if would produce some vapors or gas, we will classify into 1A. And if it only produces something with concentrated sulfuric acid, then we say these are the anions which would fall in the group 2. This we have already discussed about. And similarly, and here we talked about in the group 2A, these are being discussed on the basis of precipitating reagent. You just would want to precipitate them out. And lastly, we said about their redox behavior. So although most of the books are classifying it like this, but in final exam you have to take a call yourself, that in the exam which way the question is being framed, whether the precipitation is being done first and then the precipitates are dissolved, or first acid is being added so that any anion which can evolve out gases can be segregated out, and then thereafter the precipitation is being done. So I think I made my point clear. So as regard to the last discussion where we talked about that when dilute sulfuric acid is added, so these are the some of the anions which eagerly, because these are relatively basic species. So basic anions these are. So these basic anions on reaction with H positive, just like carbonate and bicarbonate eagerly would react with H positive and produces carbonic acid, which is a thermally decomposable acid. It would evolve out carbon dioxide. So from here we can do the testing of carbon dioxide. Similarly, bisulfite and sulfate, bisulfite and sulfite ion would produce sulfurous acid, and this on decomposition produces SO2. So here you can see this is colorless and odorless, but in contrary, this is colorless, but it would have a smell of burning sulfur. Smell of burning sulfur is somewhat like when you see somewhere a car tire is burning, a soot is coming up, a peculiar type of smell is coming from the burning of that tire, because it contains some amount of vulcanized sulfur is there in the rubber. So that type of a smell, if you just would want to feel it with me, that what type of smell the burning sulfur is. Similarly, if you have sulfide ion also do react with H positive to form H2S. This again is a colorless. Again, it would have some smell, rotten, egg-like smell, peculiar, dirty smell, which you might have seen in your practical while doing the practical based on the cation analysis. In the KIPS apparatus, we do form this from FeS plus sulfuric acid treated with some mineral acid. So this tend to produce what you call it as H2S. And this thiosulfate ion also do the same thing, that this again react with H positive and produces this thing, sulfur plus, and this would provide turbidity, and this turbidity disappears when you simply would heat, because SO2 would gas would evolve out and turbidity vanishes. And the point here is NO2 negative is also a species which tend to behave a basic nature, in the sense that it can react with H positive to form nitrous acid, which easily can get decomposed to produce brown gas. So the point here is that these are the anions which I have grouped it here. If you treat it with dilute sulfuric acid, they tend to produce some gas. The gas can be colored, then if the gas is colored, it is NO2 negative. If the gas is colorless, any of these 6 anions are there, and out of these 6 anions, if something is producing a peculiar smell, then it can either be sulfide or sulfite or bisulfite or thiosulfate. And if it is not producing any smell, then carbonate or bicarbonate is there. Now we have to segregate them. If you have, so that is what we are today working on that. Also, I do say here is it is better to remember all of these gases first, that because time and again we will be using this as one of the way of identifying the redox reaction. Just like if in during any process, just like if I would write it here, sulfite, bisulfite, okay, excuse me, I should write it, bisulfite, sulfite, thiosulfate. These are the species which when put into H positive produces SO2 gas. And now you need to understand it this way, that what are the things which can be shown with SO2, because as the SO2 gas is evolving out, what can we do to confirm it? So SO2 is a colorless, smell of burning sulfur, slightly acidic in nature. This is the flow chart. This way you should remember it for a longer duration of time. So treat it with some oxidizing agent, because it itself is a good reducing agent, because it is in plus 4 oxidation state, it can go to plus 6. So it turns purple KMnO4 to colorless or slight pink, dichromate green, orange to green, it can convert. And similarly, ferrous sulfate, any ferric salt like ferric chloride, because all of these are acting as an oxidizing agent. So this here you only remember it, because this is the best way that you could address the thing, that anywhere during the qualitative analysis, if SO2 gas is being produced, it can be confirmed with any of these three, any of these oxidizing agent. So KMnO4 turns to light pink, dichromate turns to green, ferrous chloride turn light green because Fe2 positive is light green, bromine get converted to bromide, iodine to iodide, iodate to iodine, and the SO2 get converted to sulfate, that is in plus 6. Balancing is not required, but only simply you should know which oxidizing agent when on conversion, because make it a point, SO2 reacts with H2O2 as well, but during the process of SO2 reacting with H2O2, there is no observable color change in the oxidizing anion. So make it a point. This also is very important to address here with, that the oxidizing anion which you are adding to SO2, that oxidizing anion should change its color, because SO2 in itself is colorless, and if you add a oxidizing agent which is colorless and the production of the product which are being produced are also colorless, then we are not able to detect it. So this is the point always have to remembered with. Another thing which you should also focus here a bit of from the P block, in the P block SO2 is there in our syllabus. So H2S also could act as an oxidizing agent, just like if you treat SO2 with H2S gas. H2S gas is there in the qualitative analysis which we are going to discuss in a while. It changes to sulfur along with the I think you do produce here water. It get converted to this, and balancing you can do it. So the point here is it is in plus 4, this is in minus 2 going to 0. So it's a case of COM proportionation. So this reaction is also very important. And lastly, SO2 is showing bleaching action, which is a temporary because of the evolution of nascent hydrogen, because nascent hydrogen when get absorbed onto a particular substance which is to be bleached, with the atmospheric oxygen, this nascent hydrogen slowly keep on reacting with, so the bleaching done is temporary. And these are the two ways by which you can produce SO2 this is one of the two methods of production of SO2. So this is one point which I wanted to discuss here, especially the oxidizing point. This is very, very important, where SO2 is acting as an reducing agent. Similarly, if I would move on to the next one, because that is the H2S, which is again very important, it is having a colorless, rotten, egg-like smell. Where it is, yes, colorless gas, rotten egg-like smell, poisonous if inhaled for longer duration of time, and as a reducing agent. Now this is again very important, as a reducing agent, because here the sulfur is in -2 oxidation state, so it cannot go further down below it, so it would act as only as a reducing agent. So as a reducing agent, it can react with number of oxidizing agents, just like the one which we have just said about. And here the sulfide would change into sulfur, Cr3 positive, and sulfur. Iodine or iodate, not iodate, this is I2 plus I negative, which becomes I3 negative, because this get enhanced in the presence of Ki. So this again changes to I negative, this to Br negative, this to you can say sulfur, and here it would, because here you always have to remember that sulfur is in -2 oxidation state, so it would bring the things down, and hydrogen, because it is acting as a reducing agent, so this would act as an oxidizing agent, where oxygen is in -1, so this changes to water. Similarly, if I would go on to this side, now this is a very important reaction where H2 is reacting with chlorine. It would not give you chloride ion, it is somewhat different, which we are going to discuss in a while. So this can change into NO2, and here it can change into sulfur is in +6, it can roll down to SO2, it can decrease to SO2. So this is some of the things which you always have to keep it in mind. So the point here is that, as I said a few minutes back, that these are some of the things which you have to keep remembering here, is that H2S and chlorine, this reaction I was referring to, is a quite an important one. Let me show you what I am trying to say here. H2S plus chlorine actually would change into HCl plus H2SO4. So this is very, very important, and some amount of water is also required here. So in the process, I do see here that sulfur oxygen is 4, so 4 water is required, and this would change into 1 sulfuric acid, and I think 6 is required here to make it balanced. So 8, 9, 10 you shall be, so 2 waters are required, no, 2 sulfuric acid, so it got balanced also. Hydrogen, yes, it got balanced. So the point here is a important, because chlorine is a strong oxidizing agent which converts sulfur to sulfate, sulfide to sulfate, sulfide to sulfate. This is very, very important in the presence of chlorine. Unlike the case of bromine, where if you treat H2S with bromine, what you end up getting is sulfur plus 2 moles of HBr. Here the point is, chlorine is a stronger oxidizing agent, which you always have to keep it in your mind. Now coming on to the specific testing. As regards to the specific testing, if the system is containing carbonate and bicarbonate and you want to distinguish them, so make it a point, the best distinction way is the precipitating reagent, because we know for sure that bicarbonate salts are always water soluble, and if you treat it with precipitating reagent, there is no reaction. If on adding of any of these precipitating reagent, there is no change in color, no precipitation happening, so it means bicarbonate. And fact of the matter, how do I come on to this conclusion is, first I might have treated it with H positive, which in a way produces carbonic acid, which produces a colorless gas, carbon dioxide. Now once some colorless gas is being evolved out, I am able to get that the system may have carbonate or bicarbonate, and this can be precipitated in this fashion. AgNO, if carbonate is there, then precipitating reagent AgNO3 gives white precipitate, barium chloride white, And these are the three important in particular to precipitate carbonate ion, because these are going to precipitate and give you basic carbonate. These are going to give you basic carbonate. So this can be a important question for a MCQ, that if a system is containing carbonate and bicarbonate and you are adding, let's say, mercuric chloride, what type of precipitates you would get? A reddish brownish precipitate which is of the basic carbonate. So one way is precipitating reagent is quite important. Another is preliminary, you can go with the phenolphthalein also. If you just would take the salt directly, take its aqueous solution, add phenolphthalein into it. If it turns pink, if the pink color comes on simply adding taking aqueous solution, adding phenolphthalein into the carbonate bicarbonate solution, it must be containing carbonate ions. Why? And if no pink color, so I will say, or light pink, intense pink is not coming, or no pink color is obtained, so it can be said as the presence of bicarbonate. So if pink color is coming, so it means carbonate is there, simply because of the fact that the carbonate ion hydrolyze more as compared to it will make the solution more alkaline, because if the pH is above 9 or 10, the intense pink color is evident with the phenolphthalein. So here the point of the fact is that we just have said basicity of carbonate ion is more than that of bicarbonate. So aqueous solution would be more alkaline and would give you intense pink color with the phenolphthalein in the case of carbonate ion. This I already have talked about the precipitating anion. Here I said these are very important because these are basic carbonates. So you can be asked a direct question, which among the following carbonate is basic carbonate? So zinc carbonate, because it would be when precipitated it would get zinc hydroxide along with, just like in the copper also, and in the mercury it get precipitated as carbonate along with the oxide. So coming on to the next point is the phosphate ions. And one more thing, if you just would analyze, because silver nitrate test is quite an important one, and if you just would want to distinguish between these two, that can also be evident. Silver nitrate you just add, if you would get silver carbonate as some residue as precipitate is there, so I will say carbonate is confirmed. And if you heat them, it will give you white precipitate and evolution of carbon dioxide. But if this is in the this would be there in the residue, and if in the residue you would not find any sort of precipitates, then the filtrate might be consisting this thing: bicarbonate, silver and nitrate. And if you filtrate on heating gives you this white precipitates, so this means it would be carbonate, bicarbonate in it, because bicarbonate on heating changes to water and carbonate. So this you always have to remember. So this is quite important to let you know. So because once this silver carbonate is being formed on heating, it will change into Ag2O. Now the point here is that or if these two are formed, put that into ammonia, this get dissolved to give you clear solution, because almost all salts of ammonia dissolves in, all salts of silver dissolves in ammonia, except two cases which we are going to discuss in a while. Okay, now coming on to, the video may go in length because we have to analyze all of these anions in length. So sulfite and bisulfite, out of this, sulfite is more of a alkaline. It would turn litmus paper blue because it is alkaline, and this is almost neutral because it is not so basic. And again you are supposed to use the precipitating reagent. Any of these precipitating reagents can be used. Among this we will be saying that silver nitrate precipitation was the important one. This is the most important one. We would be analyzing this in length. So one is, or you can say calcium sulfite or strontium sulfite. Basically what I am trying to explain it here, most of the time you have to focus on these two precipitating anions, precipitating reagent mainly. Bisulfite ions, just like bicarbonates, give no reaction. They will remain in the filtrate as water soluble thing. Okay. Now coming on to the specific, in specific you have three things with you. As I said, one, silver nitrate test is important for the sulfide. Second is reaction with zinc and sulfuric acid. This also is quite a important one. And last one is this: first you add some oxidizing agent, then precipitating reagent, or precipitating reagent. And so let us discuss all of these three one by one for the detection of sulfite ion in particular. So first is silver nitrate. So you can get some question, as I'm saying, silver nitrate is always very important because silver nitrate almost precipitate most of the anions. So the point here is, if sulfite ion is in excess, it makes a species of this nature which is soluble. This would remain soluble. So this is a very popular question. Silver nitrate added to excess of sulfite ion, the solution would remain soluble. But if silver ion is in excess, then it get precipitated. It get precipitated. Now the another thing, this precipitates on heating. If you just would heat them, what shall you be getting? So in the first case, if you take this soluble salt and just have heated it, it would evolve out along with SO2 gas. Silver plus SO2, silver got precipitated, and along with you would get SO2. Here basically in this case you would get silver along with H2SO4. So this again is a very important viewpoint to keep it in mind. Okay, and if I would move further, here you also would get sulfate ion along with. Now if I move further, that in the case of second case, when you add zinc, zinc is in zero oxidation state, it is acting as a reducing agent. So this means this must be in the +4 oxidation state, it must be acting as an oxidizing agent, isn't it? If you have to think it carefully. So sulfite ion reacted with zinc, zinc will change into Zn2 positive, and this sulfite, where sulfur is in +4 oxidation state and is acting as an oxidizing agent, it produces H2S gas. Balancing is not required and not to be addressed here with. In particular, if something is asked, you can do the balancing from the redox balancing point of view. So H2S gas is being produced. So here this can be detected then. If H2S gas is being produced from the sulfite ion, not from the sulfide, I can make it from the sulfide also, but if sulfite is being first preliminarily it is investigated that it is producing a SO2 gas with a smell of a burning sulfur, then we can go this way. So this particular discussion we already have done with, that H2S is in -2 oxidation state, it turns KMnO4, K2Cr2O7 or iodate or bromine water or chlorine this changes to Mn2 positive. Observable color change would be there in the oxidizing agent. So it would change to Cr3 positive, iodine, this is Br negative. Earlier it was brown water, which it decolorizes the brown water H2S. Or you can treat it with this one also. This again is a very important one. As I said, if right from the smell, H2S can be detected from the smell, rotten egg smell, or if moist lead acetate is being treated with H2S, it would give you PBS, which has a black precipitate, or cadmium acetate CDS, it has a yellow precipitate. So H2S can be, or sulfide ion can be also be detected by lead acetate or cadmium acetate. And this particular question I already have discussed about, that unlikely chlorine on reaction with H2S produces sulfuric acid along with HCl, where this changes from 0 to -1 and sulfur -2 to +6. Keeping this in mind, that this acting as a strong oxidizing agent, unlike bromine and iodine. Coming on to the next is the detection of sulfide ions. Now sulfide ions can be in particular the testing of sulfide ion. Already this we have spoken about, that either you produce H2S gas and then H2S gas can be detected in many ways, and this we have just spoken about. that this gives you cadmium acetate. If you precipitation, if you want to detect sulfide ion by precipitation, then cadmium sulfide, lead sulfide, this would have black precipitate, this would have a yellow precipitate, and this silver sulfide would have black precipitate, which would not dissolve in acid. That is what I was referring to. Silver salts are mostly soluble in acid, except for Ag2S, AgCl, AgBr. This we have talked about in the last video as well. These salts of silver would not dissolve in HCl. Now, in case of sulfide in particular, a particular test is there which we call it as sodium nitroprocyte test. So that is very, very important. Sodium nitroprocyte is this reagent. So how is it being produced and how is it being seen about is, let us discuss that in detail. Sodium nitroprocyte test. So basically what you always have to remember, that if I simply would write NaFeCN5 NO, so this is called as sodium nitroprocyte. This particular species is called as sodium nitroprocyte. In this sodium nitroprocyte, if you treat it with sulfide ion, what basically do you get here is a species of the type FeCN5 NOS, and here again it is just like in this case, it is 2 negative, so it is 4 negative, because if I would make its species Na2, so if I just would take sodium sulfide here, so the reaction got balanced. So this in particular has a deep purple color, or some books say it has to be having a red coloration. So both ways, intense purple or red color is being obtained if you have sulfide ion with you treating it with sodium nitroprocyte. So here, because this particular compound is very important from the coordination point of view as well, so make it a point, you always have to remember these three things in your mind, that here this is in +1 oxidation state, this is in +2, this is in -1, and this is in +1. So in totality, if you would see that sodium, if I just would write in total -1, +1, +2 and 2 plus, so in total the algebraic sum happens to become 0. So make it a point, here the 2-3 things are very important from the coordination point of view as well. For that I will be making the video as well. So this particular species has 0 unpaired electrons. So it is a diamagnetic species with a D2sp3 hybridization. So this again is quite important from this point of view. Sodium nitroprocyte has iron in +2 oxidation state, that is 3d6 system, with all the electrons paired up. And the hybridization happens to come out to be, because there are 6 ligands, so the hybridization which you happen to get is D2sp3. And another thing which is quite important, which generally people don't be knowing well in thorough. Now what is it? This particular species, when I write Na4 FeCN6 FeCN5 NOS. Now first you have to see what is this ligand. Basically this ligand is which we generally don't write that way, but I always advise my student to remember it like this, that if I just would write it this way, just hold on, yes, it should be shown it like this, because basically this is sulfide ion which happens to react the nitrite ion. This is the species, isn't it? And if I just would attack this, what shall I be getting? I be getting sulfur N, and or you can create a triple bond also, this becomes NO. And the point here is, this can undergo resonance then. So something like of this order. So the point here is, overall this then can be said as to be thionitrite ion. And in the thionitrite ion, that is NOS we generally write it, overall charge is -1. Overall charge on it is -1. So this always you have to remember. So this is overall -1. This is -1. This is +2 and this is +4. Do it make algebraic sum 0? Yes. +4, +2, +5. Sorry, -5, -5 and -1. So algebraic sum happens to come out to be 0. So this always you have to keep it in your mind that it is thionitrite ion, you can say, in the this particular species. And one more thing which you can add to your knowledge bank here is that when I just would write here that this particular species, let me write it for you once again here. So if I treat this with H2S, do it give any sort of color? That intense purple color or intense red color is achieved in this case? No. It is generally seen it would not provide that much of, because H2S on dissociation, because it would not provide you sufficient amount of sulfide ions, because SH negative then has to break down into sulfide ion. So the sulfide ion which we happen to get from H2S, directly treating it with H2S, that sulfide ions are not sufficient to bring about this coloration. So we generally say that H2S would not, but yes, any sulfide ion, if you have with you any sulfide ion, then it can give you sodium nitroprusside test. And sulfide ion can also be detected with a reagent which we call it as, or a test is named as methylene blue test. So here I just would recommend you to just remember the name. Wherever something is written as methylene blue, you should know that it belongs to the testing of sulfide ion. Otherwise it take into account a little organic entity. This organic entity reacts with sulfide or H2S in the presence of Fe3 positive, and this complex formed this cyclization of the two benzoid rings through the sulfur and nitrogen results in a methylene blue. So this is if you could remember from the organic point of view, whenever you happen to get a quinoid ring tend to provide some color. So that color, and that too benzoid, when converted to quinoid type of a ring, then you happen to get intense blue color. So this is, if I would write, this is something benzoid ring, something of this nature, and if with some reaction, if it happens to turn into this form, this is called as quinoid form, so then it tend to give you some intense color. So methylene blue you just remember as an test for the detection of sulfide ion. Okay, so coming on to the thiosulfate, this again is also very easy. First, if you treat it with the H positive dilute sulfuric acid, it happens to give you sulfur plus H2SO3, which in a way make the solution turbid, and if you heat it, turbidity vanish, because this sulfuric acid gone out of the system, removing the turbidity out of the system. Or you treat it with thiosulfate ion. At times if you treat this thiosulfate, take its ionic salt, which is sodium thiosulfate, which is commonly called as hypo. So this easily would react with iodine to produce I negative plus thiosulfate ion, tetrathionate ion. So iodine in starch, when starch is along with iodine, it is having an intense blue color, and that intense blue color disappears because it get converted into iodide, which is colorless. So this goes to 0 to -1, and sulfur goes from +2 to +2.5. So basically here in this reaction, this particular species is acting as a reducing agent. So this is acting as a reducing agent, and iodine is acting as a oxidizing agent. This also is said as to be idimetric titration, if you could recall from the topic of redox titration. But most of the time what I have found is thiosulfite ion primarily be detected with the precipitating reagent, and that precipitating reagent could be AgNO3, as I said, majorly AgNO3, and lead acetate, mercury acetate, or copper sulfate. So let us discuss all of this in detail, because precipitating reagent is very important. So there are 2-3 ways to do it. that first you just would add silver nitrate into the solution. Now once you add silver nitrate, as I said, precipitating reagent for thiosulfate ion. Now this precipitating reagent can be AgNO3, lead acetate, mercury nitrate, or copper sulfate. All of these gives white precipitate. All of these would give white precipitate as M, depending upon the valency of the metal. So it can be Ag2SO3, which I wrote it here to save time, this, or lead, or mercury, or copper. So this always you always have to remember. And if you just would heat, all of them change to black sulfide, because sulfides are generally black, leaving aside few. Generally cadmium sulfide is yellow, manganese sulfide is pink, mostly others are black. And if excess of thiosulfate is being added, so this is a very very important reaction. If excess of thiosulfate is added, it makes a clear solution of these species. Out of this, the one with the copper in regard to its formula is very very important. So this is a bit of mugging part, but it is quite important. Now what I am saying here is, first the precipitation has happened. That precipitation on heating gives you black precipitate, and black precipitate that are black only, and the other what I just have said, this white precipitate, if excess of thiosulfate is added, it gives you a clear solution. Is it okay? So this is one of the way of identifying sulfide ion. Next, coming on to, so video may go in length. Next would be the case of if I would write thiosulfate, okay, as an oxidizing agent. That I think I missed it somewhere. Yes, here. As an oxidizing agent, it can react with ferric chloride. It can react with ferric chloride, or it can react with cyanide ion followed by ferric chloride. So that two reactions are also very very important because of the point of the color change. That ferric chloride Fe3 positive, Fe3 positive treated with thiosulfate ion, it gives you a violet color, and excess of Fe3 positive then changes to Fe2 positive, making it a light green along with tetrathionate. Generally it gives this particular hypo ion or thiosulfate ion generally changes to sodium or tetrathionate ion. So here the point is, all of this you have to keep it in mind, that observable color change would be there, because if this is acting as an oxidizing agent, which is a colorless, which makes a colorless solution, but the oxidize, if it is reacting with some reducing agent, that reducing agent do show you some color change, then only it can be detected, otherwise there would be tough one. Second is KCN treated with KCN and these two when reacts, sulfur it changes to thiocyanate ion, SO3 negative goes out, and SCN negative thiocyanate ion reacting with Fe3 positive gives you RBC color. This we have done in quantitative analysis of sulfur in a organic compound. Very popular reaction it is, SCN3. This is having a red blood coloration. So these are two important things which you always have to keep it in your mind. So here what you always have to remember, I just have overlooked it. This is acting as an oxidizing agent. Very sorry. This is acting as an oxidizing agent, and this goes from sulfur +2 to +2.5. So this is acting as a reducing agent. I think I wrote it wrong. Yes, I wrote it wrong. So here it is again reacting as an reducing agent. So I think we need to mark there also. Where is that? This is wrongly written. So this is here, this is acting as a reducing agent when it is treated with FeCl3 or first with cyanide followed by Fe3 positive. So this you always have to remember, where this Fe3 positive changes to Fe2 positive, and here it changes to FeCN thrice. So this is quite important, where sulfur in +2 oxidation state goes to tetrathionate in the as an reducing agent. So here I just have wrote it wrongly. Anyhow, coming on to the next one, next one is the case of nitrite ion. Nitrate ion in reaction with H positive. First, nitrite ion reaction with H positive gives you HNO2, and HNO2 on heating may produce water, NO, and NO2 gas. And this NO2 gas is a brown colored gas from where we can detect many things. And as an oxidizing agent, it is in +3 oxidation state, and if it goes to +2 oxidation state on reaction with iodide is acting as a reducing agent, and iodine along with starch, if small amount of starch is along with, it would give you a blue color. And as a reducing agent which is very popular, it can react with KMnO4 or K2Cr27. So it goes from +7 to +2 along with NO3 negative as a nitrate, and this goes from +6 to +3 as a green solution, and here it would change into nitrate ion. And the most important for the nitrite is the brown ring test, which I am going to discuss in a while. So in the brown ring test, what basically we are going to take is, so this test is equally applicable for nitrite as well as for nitrate. So basically freshly prepared ferrous sulfate is being treated with nitrite ion solution along with sulfuric acid, and during this process what exactly do it make here is something of this, because it produces NO gas in situ, and that NO gas then react with this particular species to form this thing. Is it okay? So this you always have to keep it in mind, that this particular has a brown color. This particular complex is again has a brown color. So how is it being done? Rest of how this is being produced in situ, that you should not focus about. Here you only have to remember that there are two anions, nitrite and nitrate. Both can be detected with the brown ring test. You take a solution, onto this solution this is a nitrite solution. Into this you add ferrous sulfate, from one side aqueous ferrous sulfate freshly prepared, along with sulfuric acid, along with dilute sulfuric acid. So what would happen, as these are falling here, in here somewhere here a brown ring is being generated, and that brown ring is because of the formation of this particular complex. So that is what you call it as brown ring test. There are some other things which other anions may interfere in that brown ring test is bromide and iodide, because sulfuric acid may convert that into iodine and bromine. So that we will be taking up in the discussion of nitrate ion as well. Now coming on to the bromide, iodide and chloride. So in particular this is quite important. So bromide, chloride, bromide, iodide in particular can be separated by precipitating reagent like AgNO3, which we are going to discuss in detail, and lead acetate. And along with, you just do, because with the dilute HCl they would not react. With concentrated sulfuric acid, Cl react to form as an acid HCl, which can be detected by treating it with ammonia as a white fumes. But bromide and iodide being a strong reducing agent, good amount of fairly good reducing agent, along with sulfuric acid, they happens to produce bromine or iodine gas. This is very important. Here sulfuric acid acting as an oxidizing agent. This I told in the last video as well, that concentrated sulfuric acid better act as an oxidizing agent, and dilute sulfuric acid better act as an acid. So dilute sulfuric acid better act as an acid rather than an oxidizing agent, and concentrated sulfuric acid better act as an oxidizing agent rather than an acid. But both ways they may act in particular case. And similarly, if you treat it with Procyte along with concentrated sulfuric acid, Procyte if I treat with, it is here the magnesium +4, so +4 goes to +2, which is having a light pink color, and with the evolution of a gas. So here These are acting as a reducing agent, and this is acting as an oxidizing agent. Here also this is acting as an oxidizing agent. In chloride case it acts as an acid, but here they act as an oxidizing agent with concentrate. So from here the color of the gases can be identified. Color of the gases, brownish green is for the chlorine, and reddish brown, violet is for iodine, reddish brown is for the bromine. Now let us discuss this in particular in detail. So AgNO3 when is added, it would produce AgCl, AgBr and AgI, which in a way can be distinguished on the basis of color. This is white, this is off-white or light yellow, you can say off-white or light yellow, or this can be said as to be yellow. And you would see some important thing in this, that if you treat all of these silver halides, because this is quite important, that you would see that this is nearly insoluble, and this is partially soluble, and this is soluble. So whatever precipitation you have got out of them, if you treat it with ammonia, if you would see the thing got solubilized, so it means it only is having chloride ions into it, and anything is left in the residue can be AgI. So this AgBr would be difficult to identify with this way. So then if you treat it with any of these acid, as I said few minutes back, that AgCl, bromide and Ag iodide along with Ag2S, these are the 3 or 4 salts of silver which always are insoluble in acidic condition. So these are insoluble in acidic condition. So here with this we did few minutes back, this here it is soluble because it is going to make a complex, and this is also soluble. Here with the cyanide also it is soluble. So here it happens to give you something of this type of a anion is being generated here, and here in this case it would make a this sort of a complex. So this you always have to keep it in mind. Okay, so coming on to the next point, with lead acetate, chloride and bromide would give white precipitate, and this will PBI would have, some books says light yellow and yellow precipitate. Now in particular, out of these halides, one of the most important tests is the chromyl chloride test. Chromyl chloride test is a test for the detection of chloride ions. This is the test for the detection of chloride ions, where chloride is being treated. Chromyl chloride test. In the chromyl chloride test, chloride is being treated with potassium dichromate in the presence of concentrated sulfuric acid to give you deep blue red color, and this deep blue red color is because of the chromyl chloride, and that chromyl chloride easily get dissolved in alkaline medium to gives you yellow precipitates of chromate, or soluble yellow anion of chromate. So that is what I just have shown here, yellow color. So the point here is that Cl negative in particular, this is the test of in specific for the chloride ion. Chloride ion do react with potassium dichromate in the sulfuric acid to form a chromyl chloride, as is being shown here, if you just would want to see the reaction. Now here you need to understand 2-3 things more, that in the chromyl chloride, bromide and iodide do interfere, but these would get changed into bromine and iodine, because these are fairly good reducing agents. So being a reducing agent and this is an oxidizing agent, it convert it into bromine and iodine, so chromyl chloride is not being formed. Another thing, that if the chloride is being given by tin, lead, antimony, mercury, all of these, because these, if I would say SnCl2, PbCl2, are these be giving you chromyl chloride test or not, or HgCl2, AgCl, these would not give, because these would primarily be having more of a covalent character, because they have a predominantly covalent character, so it would not be giving you this particular test. That is what you call it as chromyl chloride test. And as a matter of fact, here you have to use this as a concentrated sulfuric acid. This also you have to keep it in mind. And another thing, that chloride, bromide and iodide should interfere in this. So these should be absent, because with the sulfuric acid, all of these get oxidized. So if they all get oxidized, so sulfuric acid start getting used up here. So that we don't want to go that way. And now chromyl chloride, this I already have said that if you just would add alkaline condition, this will turn into yellow color. Coming on to the next part, specific test of bromide. So this is also said as layer test, where a test tube is being taken. In this test tube, you just would or in any conical flask or in this type of apparatus, you just would add into this if the solution is containing bromide and iodide, you just would add chlorine water into it. Along with, you just would add some into it, and along with it, you just would add CCl4 or carbon disulfide or non-polar organic solvent. Non-polar organic solvent would also be added along with. Now, once you mix it, or once the reaction has happened, so chlorine water, this redox reaction, because if we write SRP, fluorine greater than chlorine greater than bromine greater than iodine. So chlorine is a better oxidizing agent than bromine. So this would act as a reducing agent and produce Br2 along with Cl2 negative. And similarly, this, if iodine is there, so this would change into I2 and this would change into 2Cl negative. So this is what we can do here. So what would happen is, when you mix it well, because bromine is a non-polar species, it get dissolved into CCl4, and CCl4 layer would get a brown color. So that way you can identify bromine. And if the instead of this iodine is there, that would give you intense violet color in CCl4 layer. So from the color of the layer, you can identify the presence of bromide or iodide. So this in a way is a simple testing to do that. Now, as regard to the iodide in particular, if you want to identify iodide, so there are 2-3 redox reactions. It primarily done not with precipitation. Lead acetate you can add. Lead acetate happens to give you PbI2, which has a yellow PPT. So this you can do with precipitation in particular, but majorly you would be doing it with a redox. And in the redox, this particular first reaction, where iodide is being treated with copper sulfate, which is blue colored aqueous solution, this turns to brown, which is a very popular sort of reaction. Copper sulfate treated with Ki, 4 moles of Ki. This in particular, you read it many times in different books. And then this iodine is being treated with hypo in the redox titration, in the redox idometric titration. This is in idometric titration, you might have read. And then this is changed into this and sodium iodide, if you are recalling a bit about it. So in particular, what you always have to remember, iodide is being treated with copper sulfate. This type of a brown color is being obtained, or with mercury chloride, scarlet red precipitates are achieved. And if excess of iodide is being added, this get dissolved to form reagent, which this is a reagent, Nessler reagent, if you could remember. Nessler reagent is a Nessler reagent. In later stage we will see is used for detection of ammonia gas. Or you can treat it with K2Cr2O7, which is an oxidizing agent, or KMnO4, or ferric chloride. So all of these we have already done. This is orange and this is changes to Cr3 positive, and this is yellow, and this would change into Fe2 positive. So this we have already discussed about this many times. As regard to the testing of nitrate always, as you know, nitrates are water soluble water soluble salts. If nitrate is of any metal, it is water soluble. So precipitation of nitrate would be very, very difficult. So majorly it is being done with the brown ring test, which I talked about. So this whole balancing, I just would not recommend you to remember. Nitrate ion treated with sulfuric acid, this is the freshly prepared ferrous sulfate. Why is it to be freshly prepared? That is also very important, because the problem with Fe2 positive salts is that aerial oxidation, even with aerial oxidation, it changes to Fe3 positive, which you might have done somewhere in the electrochemical phenomena of rusting. During the rusting, at the last step, ferrous changes to ferric. So the point here is that ferrous salts should always be freshly prepared. So NO gas is being generated, and this NO gas then gives you a brown color. So from that point of view, it is quite a important one you to remember in regard to the brown ring test of the nitrate ion. Then other thing which you can do for the nitrate is you just reduce it to ammonia and then detect the ammonia. So other way of identifying specific testing of nitrate is to reduce NO3 negative to ammonia. This can be achieved only with two reducing agent, aluminium in alkaline condition or zinc in alkaline condition. So always remember, these two are the good reducing agent which converts nitrogen of +5 to nitrogen of -3 to ammonia. Then ammonia can be detected, and ammonia turns Nessler reagent brown. That is one of the test of ammonia, and from its pungent smell, or there are 2-3 ways by which you can detect ammonia. So this is what I was referring to. So there are two reducing agents which you can market here. One is zinc in alkaline condition or aluminium in alkaline condition. So balancing again is not required. Majorly you should be knowing that nitrate detection can be done through the conversion of nitrate to ammonia, and then ammonia is being tested with any of these ways, which I am marking it here. So it turns Nessler reagent brown. So it's a pungent smell, turns, because it is a little bit of alkaline, so it turns blue. With HCl it gives white fumes, otherwise it turns Nessler reagent brown. So that is very, very important to remember with. So this is a anion of Nessler reagent. This is Nessler's reagent. On turning to the brown, this compound can be asked. So this you have to remember, there is no other way around. Now coming on to the last or second or third last is the phosphate ion. Phosphate ion majorly be identified with the way of precipitation only. In the precipitation, one is AgNO3, where it gives you yellow precipitate, or barium chloride white precipitate. These are two things, and in ammonia it dissolves. All the, as I said number of times, all the salts of silver are soluble in ammonia except AgI and Ag2S. These are the two species which generally would not dissolve in ammonia. Now the point here is that most importantly, the phosphate ion detection would be done with the help of this particular special reagent, ammonium phosphomolybdate. You need not to remember its balancing, only remember that if you get any, this particular word is very important, quaternary yellow precipitate. If this terminology is there, quaternary yellow precipitate is written, it is referring to the detection of phosphate ion. So always remember that phosphate ion detection is being done either majorly with the precipitating thing, Okay, so this I just have spoken about, that silver nitrate, yellow PPT dissolves in ammonia. All the precipitates of silver are soluble in ammonia except these two. These two would not dissolve in ammonia. And as regard to balancing, if you want to see into, you can refer to this particular slide where whole of the balancing is being shown, and this is having a quaternary yellow PPT. Now coming on to KMnO4 and K2Cr2O7, for which you mostly have a good knowledge because of the presence of K2Cr2 and KMnO4 in your CBSE syllabi. So this chromate ion can be done by the precipitation. So as barium chromate is yellow, silver chromate is red, and silver dichromate is even intense red, or with the oxidizing agent. With the oxidizing agent, if you treat it with H2O2, it gives you a blue coloration of chromium pentoxide, which is having a butterfly structure, very popular reaction, butterfly structure, where unexpectedly chromium is in +6 oxidation state, and which on standing turns to green. So here is a very important viewpoint, that chromate ion, when treated with H2O2 in the presence of ether and pyridine, this blue color remain as such, it would not turn to green on standing. Reason being, this ether would make a coordinate bond with chromium and would not allow it to turn to green, which I have just shown in the next slide. So chromate H2O2, so it is in +6 oxidation state. So this again is a very, very interesting, so it would take good amount of time. I would not want to take up that much in detail. This is very, very important from the point of view of redox, that who exactly is undergoing oxidation and reduction. That is very, very interesting in this, because this is in -1, so where it has gone. So this is because chromium is in +6, here is in +6. So from just see into it and do let me know if you are able to identify it from the redox point of view, who is undergoing oxidation and who is undergoing reduction. Only hint I can give you is chromium pentoxide, where the 4 oxygen is in -1 and 1 oxygen is in -2. And this chromium pentoxide in acidic medium decomposes to green chromium 2 positive, evolving out oxygen. This is a reaction very important from the standpoint of view of redox. So both of these reactions are very important from the redox point of view, that who is undergoing oxidation and who is undergoing reduction. Otherwise, these chromate and dichromate can easily be detected by its oxidation reaction, by the virtue of their oxidizing nature, oxidizing agent. So they turn sulfite or SO2 to sulfate and itself change into Cr3 positive. And similarly, this sulfur or sulfide or H2S would change into sulfur and Cr3 positive. This you know. Fe2 positive changes to Fe3 positive. This produces bromine, this produces chlorine, and this also would produce chlorine. Here it would change into acid, this would change into nitrate, and all of these then changes to Cr3 positive. So orange turn to green. Dichromate is orange and this is green. So this already you people knew much about it from the KMnO4 and K2Cr2O knowledge. And another one is KMnO4. KMnO4 again is being identified, unlike the chromate. Chromate can be identified by precipitation, but KMnO4 or permanganate or manganate only can be identified with the oxidizing nature. So here it is in +7, it can go to +2 in acidic medium, and this will change into sulfur, Mn2 positive, which is light pink, and this changes to sulfate, Fe3 positive, I2, NO3 negative, carbon dioxide, O2, along with you would have sulfate ion. So this in a way tells you many things. And lastly, one detection you can also take, if the given salt at the very start is having an intense black color, just heat it well. If in the residue you happen to get this particular, because if dry crystal is almost black of it, it is black colored. If you on heating turns it residue, you would get as a black. Heat it well and then add water into it, and if the water contains a green color filtrate, so that means there is a presence of KMnO4 after heating on addition of water. So in a way, I almost have discussed all the important specific reactions. Here and there some mistakes may happen because of the color or some redox balancing or something like that. Please ignore it. Otherwise, I tried my level best to make the things as clear as I could. So now in the next session, we will be doing on session 1, we almost have completed anion analysis. Cation analysis would not take this much of time. Anion analysis is being done in session 1 and session 2. And in the upcoming session 3, I will be doing the problem solving, which is most important. Problem solving on anion, on acid radicals. And then fourth session would be acid radicals, on acid radical in the upcoming session. And then the fourth session is of the cation analysis. Cation analysis would not take that much of time because it is more systematic and would take much less time. Thanks a lot. Have a nice day. Hope you enjoyed the session, although it went little in length. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.